Hello students. In this video I'm going to go over two examples. I'm going to write out the constraints for question 1, and then I'm going to let you solve it, and then I'm going to go to question 20. This is a maximization problem, and I'm going to draw this out and then let you solve it. So question 1 references a material or question back in chapter 1, which we did not cover, which we don't cover in this course. So Tracy McCoy wakes up Saturday morning, remembering that she promised the PTA she would bake some cakes and homemade bread for its bake sale that afternoon. She does not have time to go to the store to get ingredients, and she has only a short time to bake things in her oven because cakes and breads require different baking temperatures. She cannot bake them simultaneously, and she only has 3 hours available to bake those products. A cake requires 3 cups of flour and a loaf requires 8 cups. Tracy has 20 cups of flour. Cake requires 45 minutes to bake. A loaf of bread requires 30 minutes, and she has a total of 3 hours to bake. The PTA will sell a cake for $10 and a loaf of bread for $6. They want to decide how many cakes and loaves they should make, formulate the linear programming model, and then solve it graphically. So let's go into, where are we? Here we go. So this is question 1. So our objective function is to maximize our profits, which is $10 for each cake plus $6 for each loaf, and we are subject to 2 constraints. The first constraint is the amount of flour we have. Question states that we have that each cake requires 3 cups of flour and each loaf requires 8 cups of flour, and we have a total of 20 cups of flour. That's our flour constraint. Our second constraint is the amount of time. For each cake, x1, takes 45 minutes to bake and 30 minutes for each loaf of bread to bake. And we have up to 3 hours. Now we can't write 3 here because the variables here are in minutes. So we'd have to then write the right-hand side of the constraint in minutes. So 3 hours times 60 is 120 minutes. This is the time. And we have the non-negativity constraints that x1 and x2 have to be greater than or equal to 0. So solve this. I will produce a video, the next video, that will go over some of these answers. So let's take a look at question 20. I'll write 20 right there. We'll go back to the course notes. Go to question 20. This lists it out rather nicely. Where is it? On page 63. Solve the following linear programming model graphically. Maximize z 1.5x1 plus x2, subject to 3 constraints, and the 4th non-negativity constraint. So let's graph this, and then I'll give you, then you should be able to solve this problem graphically. So question 1, let's put this over here so I can see this. I'm going to write out the constraints and the maximum, objective function, 1.5x1 plus 1x2. We're not sure what we're producing, but it's subject to 3 constraints. The constraints are are presented a little easier. X1 is less than or equal to 4. So that means we cannot produce 5 X1s, for example. X2 is a constraint for X2 is that X2 has to be less than or equal to 6. And the third constraint, combination of them, the sum of the two constraints has to be less than or equal to 5. So, in order to solve for these constraints, and to graph them, I should say, need to write or draw a little graph there. X1 is less than or equal to 4. So the boundary we have is going to be right around there. There's 4. So how do we draw this when there's only an X1 value? Well, basically, this just becomes a straight line. That's not very straight at all, but it's all right. So X1 is less than 4. So basically means that this side over here, I'm going to put an arrow over there. This means that it's good. Over on here, not good. X2 has to be less than 6. Let's put 6 right there. Let's make that into a 6. Draw this horizontally across. X2 is less than 6, which means anything below this section here, there or there, is good. This, basically, it's bound by the interior of those two lines. This is kind of okay, but this out here, not good. Not good, and not good. The third constraint is going to further restrict this. I'm going to draw this in a different color. Let's pick red. X1 plus X2 is less than or equal to 5. So, in order to find to draw that straight line, one way we have is that we substitute in 0 in for one of the constraints and solve for the other one. So when X1 is 0, X2 is 5. When X2 is 0, we can go back into this equation. X2 is 0, that leaves X1 to be 5. So the outermost boundary for this third constraint is 5, right around there, and 5, which is right around here. So, if I can freehand straight draw that, kind of looking okay, there it is. So this is our third constraint. So anything less than that red line is good. So basically it's saying this is good. And we move over here. This is still good. That point and this way is good. But as we move down, we come to this, our first constraint. So our feasible region, our possible solutions, somewhere in this shaded in zone here. And of course, because we want to maximize profits, we're going to find the possible answers at this point here. We'll label that A. At this point here, we'll label that B. And going straight down, we'll label that point C. So what you should be able to do now is solve or find the coordinates for those 3 points, A, B, and C, and then determine, by using the objective function, once you have those coordinates, where the best solution lies. Is it point A, point B, or point C?